So we're going to apply these properties to this third order differential equation. The general rule, let me just write down first the general rule, which will look very familiar to you. If we have a differential equation which has this general form that we've encountered in talking about the Fourier transform, sum of derivatives of the output, a linear combination of derivatives of the output is equal to a linear combination of derivatives of the input. That's the general form. What we can do is we can apply the differentiation property and the linearity property to immediately come up with essentially the analogous thing to what we saw in the case of the Fourier transform. So we're going to get the sum of AK, well, this kth derivative, when we go into hop into the transform domain, is going to give us s to the k y of s. And when we apply the transform, so I'm basically applying the Laplace transform to this whole equation. If I can use that sort of notation, it's really applying it to both sides. And on the right side, we're going to get the sum of bk, s to the k, x of s. And now I can fiddle around with some cross multiplication, and I'll get that y of s divided by x of s is going to be, so I pull the x of s over here, and I want to get rid of this so that I'm left with just y of s on this side, is going to be the sum of bk s to the k divided by the sum of ak s to the k. So actually it looks exactly what we found in the Fourier transform case. Again, plug in s equals j omega, and it's exactly what we've got for for this ratio. But I should point out, if we are thinking of this as the input and output of an LTI system, then what we know is that from the convolution property, if h of s is I'll just write it over here. If h of s is the system function of our system, and we're putting x of t in and getting y of t out, and they're related by this differential equation, that means this input Laplace transform is x of s and the output is y of s. What we know is that y of s, because of the convolution property, right? Y of t is the convolution of x of t with the impulse response of this LTI system. That means it's going to be x of s times h of s. And so what we've computed here is actually h of s. So we've actually figured out what the Laplace transform, the system function, is for that corresponding LTI system. And so now we can apply that to a specific example. And it just boils down to doing exactly the same sort of things we did when we were analyzing the frequency response of a stable causal LTI system. We basically apply this conversion of the differential equation into an algebraic equation. And then we use partial fraction expansion to put it in a form where we can actually figure out what the impulse response is. So this is a third order differential equation. And on the right, we've got second order derivative of the input signal. Oops. Okay, so now when I go through this transformation to the algebraic domain, I'll just show you exactly what I get for h of s. it's going to be 2s squared plus 5s plus 5 divided by s cubed plus 4s squared plus 5s plus 2. And when I go through the factorization, I'm just going to worry about factoring the denominator. I get something that looks like this. So this one is actually a little bit different from most of the examples we've seen because I've actually got a term in the denominator that's squared. So this tells me I have a pole at s equals minus 1 and a pole at s equal minus 2, and this is actually a second order pole. So in general, when you're talking about poles, we haven't seen examples of that yet, you'd actually have to talk about the order of the pole, and when you draw the pole zero plot, what you would do is you would put a dos Equis. You put a double X so that you know it's a double pole. It's a little bit hard to tell, but in textbooks they make it pretty clear. Or you could just put the order of the pole, indicate that it's a second order pole. Okay, at minus 1. And now we just go ahead and we proceed with our partial fraction expansion of this guy. It's a little bit more, you have to be a little bit careful when you do that, but you can figure it out essentially using the same techniques we used in the examples we've looked at. And I'm just going to show you what the result turns out to be for that example. Turns out to be that I can rewrite h of s after using partial fraction expansion as 2 divided by s plus 1 squared minus 1 over s plus 1. So notice we have terms that have all of the powers of that term corresponding to the second order pole. So we have a first order term and a second order term in the denominator. And then it's plus 3 over s plus 2. And now what we do is we go to the table. And the table is table 9.2. That gives us our transform pairs. So LT pairs. And that table is also in the book. So it includes a number of useful examples. And the ones I want to point you to, though, are ones that look like this. So this one we're already familiar with. 1 over s plus a. We know that gave us a right-sided exponential and a left-sided exponential with the corresponding right-sided and right half plane and left half planes. But then you have these others that include the higher powers. And they look again like these exponentials, but you've got these factors that are powers of t in front. And so we can just use that to tell us how to invert each of these terms. We can see that what I didn't mention is that I was assuming that this LTI system described by this equation is a causal one. Why do I need to tell you that? Because that's going to help me figure out what my region of convergence is, and I need that in order to figure out how to invert this. So in this case, because it's causal, it's got to be this right-sided region, and I'll use the fact that the region of convergence, because of that causality, is precisely that right half plane. Now I just go to my table and I can conclude that my h of t, just by using that, turns out to be 2t e to the minus t. That's from this first term. The 2 is from that constant, and the t e to the minus t is from the 1 over s plus 1 squared. Minus e to the minus t, of course there's going to be a u of t that I throw in for all of these. Minus 1, this is the e to the minus t, and this is going to be plus 3 e to the minus 2t, and they're all going to be multiplied by u of t. Okay, so that's the game we use when we're analyzing systems that now that we know enough, we can actually, I could have considered the possibility, I could have said, look at the LTI system that isn't causal, but maybe that has, maybe I would tell you that it's got a two-sided impulse response. Then you would know that this was the region of convergence, and you'd have to take that into account by using these results to say, well, you know, this term it's going to be that half plane, and this term it's going to be that half plane, and so on. Okay, so that probably is seems fairly routine now for you. And what I want to do in the remaining time is now apply this stuff to analyzing our audio system, our feedback system. So we're in a position now to look at a lot of the architectures that we've looked at involving LTI systems and be able to say what the Laplace, the system function is for those different systems. So for example, we have a serial concatenation. Serial concatenation is where we have two systems, LTI systems. And the first one has, let's say, system function h1 of s. Second one has system function h2 of s. Basically, it's a application of the convolution property. What we know is that if we have x of t with Laplace transform x of s, and the output of this concatenation is y of t with Laplace transform y of s, we know that this is going to be equal to x of s times the overall system function. And a simple application, just as it's basically exactly what we did in the case of the frequency response, we're going to see that h of s is the product of h1 of s and h2 of s. And similarly, for a parallel concatenation, that one's even more straightforward. That one's going to turn out to be a way of sort of adding system functions. So if our situation was that we had an input x of t that was sort of split and fed to both of these systems, and then the result was added to produce y of t. We know that y of s is going to be x of s times h of s. And what is the h of s going to be for this whole thing? It's going to be just the sum. Now, I haven't said too much here about the regions of convergence, but because we're dealing with the convolution property, we saw that when you're doing convolution, the resulting region of convergence at the output is going to be the intersection of the region of convergence of x of t and the region of convergence of the impulse response of the system. Okay, so you have to take that into account. Okay, so this is our parallel concatenation. And now we're in a position where we can take a look at a simple feedback loop. So let me do the schematic of the feedback. System, and then we'll see what we can say about what the overall system function is for that. Now, is this pretty clear to everyone? It's basically the arguments are essentially identical to the ones we used for the Fourier transform when we were looking at frequency responses. But we didn't look specifically at the feedback system. So let me just show you the system that I have in mind. So it's going to be a feedback interconnection of two LTI systems. So x of t goes in. And there's going to be something added to it, which is the feedback. So let me give some names to these signals. Let me call the feedback, the output of the system at the feedback loop, let me call that z of t. And let me call the signal that you get by adding x to z, w of t. That w of t gets fed into this system 1, h1 of s, to produce the output, y of t. Notice that it's y of t that's fed back. So the input to that second system is actually y of t. It's the output fed back. So how do we figure out what the overall, we want to do the same thing we've done with those other cases. We want to draw a big virtual box around all of that stuff and ask what's the system function for that overall system where x of t goes in and y of t goes out. And basically, it's just, again, an application of the linearity and the convolution property. I'm just going to write down a few of the expressions, and you can confirm for yourselves that when I manipulate these things, I'm going to get the overall h of s that I show you. So w of s, well, it's the sum of these two. So it's using the same idea basically as in the parallel, not quite, but it's just the linearity. And so w of s is going to be x of s plus z of s. What's z of s? Well, z of s, we said, is what you get when you feed the output back through this second system. So that's just going to be using the convolution property. It's just going to be h2 of s, or let me write it in our usual way. It's going to be y of s times h2 of s. Let's see, what else do we need? I guess we need to figure out what y of s is itself. Well, y of s is what we get when we put w of t through the first system. So y of s is going to be w of s times h1 of s. And now we've got enough equations that we can kind of substitute, right? I can plug in, I've got this expression, I can write x in terms of z and w, z I've got written in terms of y and h2, and then I can relate w to y and h1. You put all those together, h of s, of course, is y of s divided by x of s. You use those equations to help you figure out that ratio. And what you get is the following. You get h1 of s divided by 1 minus the product h1 of s, h2 of s. A lot of times people put a minus sign here so that it's negative feedback. So they actually, it's really not just an adder, it's actually, you're negating the feedback and then adding that to the input. If you do that, the only thing that changes is that this becomes a plus. So you may see descriptions of the transfer function of a feedback interconnection where it's the feed forward system function divided by 1 plus the product of the feed forward and the feedback. Okay, so don't get thrown off by that. It's just has to do with the way you define the system.